Hello everyone, in this lecture we're going to discuss support vector machines. Support vector machines are a special category of feed-forward networks. We've seen feed-forward networks with multi-layer perceptron. The main idea of support vector machine is with data separation. So if we would like to put this in context, given a training sample, so these are the training samples, the support vector machines constructs a hyperplane that maximizes the separation margin, which is this guy, between the two classes. So when we want to separate two classes, assume that we have here a linearly separable case. So usually we draw a line between those two separable cases. However, what line or hyperplane in multi-dimension that can maximize the separation between those two classes? So why do you want this? Because the more separate those two classes are, the less we have an error. So a line or a hyperplane, the optimal line or the optimal hyperplane that maximize the separation between those two classes. So let's write this. So the main idea is to separate classes. There can be multiple classes. So we want to maximize the separation. We can call this margin of separation, rho. Margin of separation. So we want to construct an optimal hyperplane that maximizes the margin of separation. So this is what I want to do. I want to construct this hyperplane which maximizes the margin. So this notion is central for the development of support vector learning algorithm, which is the inner product kernel. We're going to talk about the inner product kernel between the support vectors xi and input x and vector x drawn from the input. So what are support vectors? Support vectors are those points that lies on the hyperplane of separation between the two classes. So we're going to discuss this issue now. So before going into those, so support vector consists of a small subset of data points extracted by the learning algorithm from the training sample. Okay, so these are the support vectors. So the kernel method is basic to the design of a support vector machine, and it's optimal. We're going to study this optimality in this lecture. Support vector machines are used for classifying difficult problems. So if we take a look at this figure, so we want to consider, a training sample. As with any machine learning algorithm, it's a supervised learning algorithm. So we have input data and the desired output, where I goes to 1 to n. Okay, we assume we have two classes. So we have di can belong to +1, or di can belong to -1, and they are linearly separable. the case of non-linearly separable pattern, we're going to discuss them later. So the hyperplane, this hyperplane that we're going to discuss, the hyperplane that does the separation is as follows. Is defined as, so as we know, the hyperplane in 2D is a single line, in 3D it's a plane, and so forth. So given that this is the hyperplane of that we want to separate, we can write two conditions. So what are the two conditions in this case? So if this is actually the hyperplane that separates those two classes, this means W2xi, which are the data set, plus b should be, if it's greater or equal than 0, implies di is belonging to the first class, and if W2xi plus b is less than 0, implies di is equal to -1. So this is the basic separation between those two classes. So now, what do you want to do? So what we're trying to do, we want to maximize, find the optimal weight and bias that maximizes the separation rho between those two classes. So we want to find optimal weight and of course and the bias WO and PO that maximizes the separation, the margin of separation, which is this guy here. We want to maximize the margin of separation. So we're gonna say we have omega O dx plus b of O should be equal to 0. This is the optimal hyperplane in this case, and this creates a discriminating function which discriminates between those two classes. Discriminant function, I'm gonna call it g of x, which is equal to gx plus b0. So this discriminating function discriminates between the plus and the +1 and the -1 classes. So now let's talk more about how can we know if a point belongs to the positive side and the negative side. That is, we want to know the decision rule when we present by an input xi, if this should be labeled as a minus or as a plus. So the way we do this, the way we find out if it's a positive sample or a negative sample, is through projection on on the weights. So if we draw the weights vector, it's going to be perpendicular to my optimal hyperplane. So I'm going to call this vector W, and I draw another vector which is called U, which is the vector to the data point taken from my data set. So as we know with the projection, when we want to find the dot product between those two vectors, it's equal to the magnitude of W times the magnitude of U cosine theta. So if we take the projections, as we know, as the angle increases, the distance, this is theta, decreases, and increase. As the distance decreases, the angle increases, and similarly, we take the projection again, and we have a larger distance. This is W, and this is U. Then here we have a smaller angle and a larger distance. So the larger the distance is from the origin, the more it's a positive, belonging to a positive class, and the smaller the distance is, it's belonging to a negative class. So the distance here is equal to the multiplication of W and U over the magnitude of W times the magnitude of U cosine theta. I just taken the dot product and place it as a form using the projection to express the distance. So the magnitude of U times the cosine theta is the distance to that point. So to further elaborate on this manner, we can say, so W0, which is the optimal hyperplane, times U is greater or equal to C to be in the positive domain, or in this case di equal plus 1. So what I'm saying here, if the dot product between W and U is greater than a certain threshold C, this means this belongs to the positive samples, and similarly if it's less, then it is belonging to the negative samples. So this implies I can write the decision rule, which indicates that if I have W0 dot U plus B0 is greater or equal to 0 to be on the positive side. From where I get this, if I say let B0 equal minus C, so I can substitute for B0 here. So I bring the C to the other side and then have W0 dot product U plus, well, minus C is greater or equal to 0. So here where B0 is equal to minus C. So now the question becomes, what is the optimal way, optimal values for W0 and B0 to have this separation? So to go around this, we need to go ahead and write the conditions or separate the classes between X positive and X negative. So let's say these are the class where we have X plus positive samples, and here we have X minus, which are the negative samples, each on the different sides of the hyperplane. So if I know what are the positive samples and negative samples, I can write something like this. We have the optimal weight dot X plus B0 should be greater or equal to 1 for di equal plus 1, and for the X minus case it should be less than equal to minus 1 for di equal minus 1. In this case, this is the positive sample, and here we have the negative sample. So I can combine those two conditions by writing di weight optimum. Of course, here we have the transpose. X plus B0 should be greater or equal to plus 1. So this condition is equivalent to those two conditions, because if I have D plus 1, this will be equal to, greater or equal to 1. If this is minus 1, then I multiply both sides by minus 1 and it changes. So points, so this is for points belonging to the positive sample and the negative sample, and we have Ti times omega 0x plus B0 minus 1 equals 0 for input that are on and in between the two lines. So everything that is on here or between the two lines, this means they satisfy the equation di W0 Tx plus B0 minus 1. So starting from here, we can say W0 transpose Xi plus B0 is equal to plus 1 for di plus 1. For these are for the data points that are called support vectors. As I said before, support vectors are those points that lies on the lines that are the furthest from the data set on the positive side and the negative side. So whenever we have points that are on the lines, they should satisfy the below two constraints. X plus b0 is equal to -1 for di minus 1. So these are the support vectors. So these are typically few points. So if I draw the line again, so points that are here, these are called support vectors. All other points are irrelevant for us in this case. Irrelevant. So in the purpose of creating a optimal hyperplane, we want just those support vectors to construct the optimal hyperplane, because I want to find the maximum distance between those two cases, and I want to maximize this maximum distance. So now in my task to find the maximum separation between those support vectors, I take the two cases where I have positive samples and negative samples. I labeled the points on the support vectors with the circle and the square for the positive and the negative. So now what I want to do is I will draw a vector here to the negative and another vector to the positive. And now my task is to find this the points that maximizes this distance. We will use the unit vector of value of w, since the magnitude of w is irrelevant in our distance computation, and w here is the perpendicular. This is w, okay, and the distance between x minus and x plus can be typically written as follows. So the width of this between the two lines is as follows. We have the difference between x plus minus x minus times this weight vector. And as we said, we use the unit vector of w because it's irrelevant for our distance computation when we use with projection. So to find the distance between the two vectors x minus and x plus, we compute the dot product between the vector and a unit vector that is normal to the hyperplane, and the unit vector that we have that's normal to the hyperplane, which is w. So since these points lies on those lines and they are support vector, the following condition holds. Which is, okay, let's write it in the, okay. So di times the optimal weight times xi, of course, plus b0 plus 1 is equal to 0. Sorry, here it's minus 1 because we take it from this side to here. Okay, so di w0 transpose x of I plus b0 minus 1 should be equal to 0. So this is true because they are support vectors. Now, so as we said, we want to find this dot product. So let's go ahead and substitute for the values. So if I take, given that x plus is for di equal 1 and x minus we have di minus 1, then substituting for x plus and x minus in this equation, we get those two. So we have, remember, this is for d equal 1, d of I, and this is for d of I equal minus 1. So we have 1 into W0 x plus V0 minus 1 equals 0. This implies W0 x plus is equal minus V0 plus 1. And this is for the positive cases. For the negative cases, we have minus 1 W0 x minus plus V0 minus 1 equal to 0, implies we have x minus is equal minus V0 minus 1. So now if I want to substitute those new values inside the width, so now we have the width between the positive x and the negative x is equal to, I have wx plus and wx minus, so this will be minus v0 plus 1 and minus v0 minus 1 over the magnitude of w. This will be equal to 2 over w0, which is the optimal weight. Of course, since we're finding the optimal weight, we can use w0 just as a notation. So now we have a notion that we want to do. So 2 over the magnitude of w0 is what? Is actually the width between those two. And what do you want to do with the width? We want to maximize the width. So the problem now, which is this the width between x plus and x minus, the problem will be maximize 2 over the magnitude of w0. So we can do some manipulation to make it easier. This can be easier transformed to minimize or maximize 1 over w0. The 2 is irrelevant for us. We can go from here to saying, okay, you know what, I can minimize w0. So for convenience also, I will go to minimize. Instead of minimizing w0, it's equivalent to saying I want to minimize half w0 squared, which is equal to half wto wo. Okay, so this way I can get rid of the square root later on, and the half is just for convenience. So what's my problem now? The problem is formulated in a different way. The problem will be given x of I d of I for I equal 1 to n. This is my training sample. I want to minimize my function, which is 5w, which is equal to half w, which is subject to, this is my constraint, di wt xi. This is the hyperplane for the positive and the negative for I equal 1 to n. So this is constructed as a non-linear optimization problem. So this is a non-linear optimization problem. That I need to solve, and we know that we can that the problem is convex, and the way we can solve non-linear optimization problems is using Lagrange multipliers. You can go ahead and check what are Lagrange multipliers and how can we use Lagrange to solve this kind of optimization problem. So typically we take we construct the Lagrangian function. So from here, let's go to the Lagrangian function. So here we are now solving the optimization problem using Lagrange. So I'm gonna call the Lagrangian function, which is now is a parameter of the weight, the bias, which these are my two unknowns, and now a Lagrange multiplier alpha. It's equal to half W, and now I multiply alpha by my constraints, and since we have here n constraints, so I'm gonna go ahead and do the sum for them, minus summation for I equal 1 to n for alpha I di wt xi plus b minus 1. Remember, here we have n constraints, so this is the summation came across. Remember, here we just have a single constraint, but these are for all n's, so now this for all n constraints. And remember, alpha I is the Lagrange multiplier. So to solve this, we need to take the partial derivative and equate it to 0. So we take the partial derivative of the Lagrangian function. First, we take it with respect to our first value, which is w, and set it to 0. And this is condition 1. So here we have, this is equal to weight minus, so we're differentiating with respect to w here. So here the half goes, and we have just the w, and inside the summation the derivative goes inside, and now I have the weight goes, of course the remaining is 0, so it will be alpha I di xi, this is equal to 0, implies the first condition is as follows: the weight should be equal to alpha I di xi. So this is my first condition. Now for the second derivative, I'm going to differentiate with respect to b, and I'm going to equate it to 0. So of course this will be 0, and here it's the only b I have. This implies that the summation for I equal 1 to n for alpha I di is equal to 0. So this is my second condition. First condition, and this is my second condition. So now, some notes on Lagrange. We know that Lagrange only works with equality constraints. Okay, so this means it's important to transform this to indicate that we only want to take the parts of these conditions where it's equal to 1, and the part where it's equal to 1 is for the support vectors, and this is what we're gonna go through. So let's write this. So Lagrange works well with equality constraints. It's a known fact. So in this case, alpha I plays an important role. Remember, we have this formula here where we multiply the condition with alpha I. So in this case, we assume that only the multipliers have to have non-zero values for support vectors, and the remaining should be 0. Well, instead of assuming, we should set them actually. So in other words, the multiplier should have the below condition satisfied for here alpha I not equal 0. The remaining alphas are set to 0. In this case, I only take the conditions which satisfy the above equality, and this is, in this case we have the alpha I relating to the support vectors. So implies use only support vectors. So let me repeat this idea. So as I said previously, we have this condition which is for greater or equal. This is not an equality constraint. It's greater or equal. The only way it's equal is when we are using support vectors and the points are on the lines. And this is what's important to us. We want just the points that are support vectors. And to do this, we can enforce this by setting the alphas to be 0 for the cases that we don't have an equality, and non-zero for the cases where we have an equality which is related to support vectors. And this is how we can solve this problem. And this is what I'm saying here in this part. So now, we still haven't solved the problem. We're just describing the problem. So a nice way of solving this problem is that we notice that here we have a lot of variables. The way to formulate this problem is to actually find the dual instead of finding the primal. So this is the, as we described the optimization problem, this is what we call the primal. So we can find the dual, and the advantage of finding the dual is actually lowering the number of variables that we're trying to find. So as you can see with the Lagrange function, we have W, B, and alphas. So it's a W and B. So now instead of finding W and B, we find alpha with the dual. So the dual is nothing like, if you want to find the minimum of the function, probably we can change the problem to find actually the maximum. And if the solution is optimal, the both of them, the dual and the primal, meet at a point which is the optimal solution. So primal function, primal, which is in this case the minimum solution, will be equal to the dual, which is finding the max of a different variable, if it is optimal, if we can find an optimal solution. Okay, so let's try and find what is the optimal, what is the dual function and what's the primal. So as we said, what we were trying to do is we had phi of W0, which is equal to the Lagrangian function of W0, B0, and alpha 0, which are all the optimal values of W0, B0, and alpha 0, which is minimize with respect to W, J of W, B, and alpha. And of course we have W is equal to I equal 1 to N, alpha I, di, xi, and summation of I equal 1 to N of alpha I, di equals 0. Now our solution should satisfy both equations. Okay, so now constructing the dual, we try first to substitute the values of these inside the primal solution. This is the primal. So if I place J of W, B, and alpha, it's equal to, if I write it in the expanded form, for alpha I di, summation I equal 1 to N, alpha I di plus summation I equal 1 to N, alpha I. So what I did is actually I expanded the summation, so I can substitute now for W's, and of course I can set alpha I di equals 0. So this will, according to this equation, will be set to 0. We have also this alpha I di, this will also be set to 0. So now what I'm left with is the following. So after substitution, we have WTW is equal to summation I equal 1 to n alpha I di WTXI, which is equal to summation I equal 1 to n summation j equal 1 to n for alpha I alpha j di transpose transpose scalar dj xi transpose xj. So this is the new function. Let's call this function the dual, which is j of w b alpha is equal q of alpha. As you see, we're gonna substitute for alpha. Alpha is now the variable, and now alpha is equal, q of alpha is equal summation of I equal 1 to n of alpha I minus half summation I equal 1 to n j equal 1 to n alpha I alpha j di dj xi transpose xj. So this is the new dual function that we want to find a solution to. As you remember, we take this out because of this condition. We substitute for w. Here we have we multiply w twice, which yields this double summation, since we have w and w transpose for I and j, and this is how we arrive to this formula. Now, what becomes the new dual function? So let's write the new optimization problem. So that the new optimization problem of the dual will be, what we want to do, we want to maximize, previously we were minimizing, maximize q of alpha, which is equal summation I equal 1 to n, I'm going to write it again, minus half I equal 1 to n, j equal 1 to n, alpha I, alpha j, di, dj, xi transpose xj, subject to, these are the equality constraints. We have summation I equal 1 to n, alpha I, di equals 0, and alpha I should be greater than 0 for I equal 1 all the way then. So this is the new optimization problem that we need to solve. This is the dual. If we find alpha, we can find the solution for the primal, which is finding the optimal weight and optimal bias. Now, what this transforming to the dual have the advantage of, now we have the dependency on xi, xj. As you see, we have no more the w variable in the equation. So actually, the dependency now, it's purely dependent on the input pattern in this case, which is xit xj, okay, for I, j equal 1 to n for all the patterns. So however, support vectors are a subset of this sample. So the support vector, remember, these are the points that are on the boundaries of the near the optimal plane, on the boundaries of the optimal hyperplane. So support vectors are only a subset. This means we have a sparse, not very much populated solution vector. And remember that all other points other than the support vectors, have alpha equal to 0, because we need only to maximize the margin of the optimal hyperplane. So in this case, once we have alpha, let's say we still didn't solve this problem. So let's say assume that we solve it now. We're gonna go over how to solve this problem. So let's say we found alpha in a way. Now, if alpha, optimal alpha is found, then I can get the weight using this formula. To ns, where ns is the number of support vectors. Alpha 0, alpha for I, di xi, where ns is the number of support vectors. Okay, and the Lagrange, and alpha 0 is the Lagrange multiplier, all non-zero. Alpha 0 I is the Lagrange multiplier for all are non-zero. Okay, now the bias can be found using this formula. What about, so we found the W, we need the bias. So we have di optimal weight times x transpose plus b0 minus 1 equals 0 implies b optimal equal minus omega optimal x of s, where here x is, denotes the support vector for d of s equals 1, implies we have 1 minus summation I equal 1 to ns alpha O. Now we substitute for w optimal di xi of t x of s, where s is the support vector. So this is from the dual we find alpha 0. From alpha 0 we find w0. By w0 I mean w optimal, and then we can find the optimal case, the optimal bias. Now this is for linearly separable points. So what about non-linearly separable points? Separable points. So in this case we have some misclassifications. So we want to find the optimal hyperplane that minimizes the probability of classification error average over the training samples. So the margin of separation between classes is said to be soft if a data point xidi violates the below condition. So let's talk about violations. So we say separation is soft if I have a violation of the below rule, which is di wt xi plus b greater equal to plus 1 for all I equal 1 to n. So how this is done graphically? So let's say we have, this is the optimal hyperplane and this is the weight. So let's say this is the positive and this is the negative. So let's say we have, so in theory all the points should be here. We have points here. But what if we have a point here? Okay, or even a point, let me write in a different color, point here. Okay, so this point here, it's correctly classified however it's not above the line. So this is a violation of this above rule, because remember this is 0, this is plus 1, this is minus 1. However, with this is wrongly classified since it is closer to the plus domain, since it's to the negative domain. So this circle is misclassified as belonging to the positives, whereas this square is correctly classified with the positive, but it's also violating this rule. So these are the two cases where we have a violation for points, and we see here we have non-linearity with separation. So how can we overcome this non-linearity? We need to introduce a slack variable. So this slack variable is introduced in the condition. So solving for non-separable points. So in this case we introduce a slack variable, and this slack variable is as follows. Now this slack variable is introduced into the constraints di. I'll get the xi plus b is greater or equal to 1 minus c of I, where I is equal 1 to all the way to n. So as I said, ci is the slack variable. So what do you mean by this? It is a measure of deviation of the data point from the ideal pattern. So a measure from the deviation of a data point from ideal condition. What do you mean by this? For if c of I is between 0 and 1, implies it falls in the correct region of separation. If c of I is smaller than 1, implies it falls on the wrong side of the separation hyperplane. So, for example, if we have a support vector, c of I will be 0, of course. So, when we have the original problem, so sum of the support vector has c of I equals 0, satisfying the equation. If c of I is greater than 0, then it's left out of the training. Support vectors are defined the same way for both linearly separable and non-linearly separable examples. Now, so what's our goal now for non-linearly separable points? Let's describe the problem again using non-linearly separable points. And in this case, what we have is we want to minimize. This is the problem for non-linearly separable problems. Of course, we have given training sample xi, di, okay, for I equal 1 to n. We want to find the weight vector that satisfies, find weight vectors satisfying di dx I plus b 1 minus c of I, and c of I greater or equal to 0 for all I. In this case, this will be transformed to phi of w, and we introduce this slack variable. We'll have wt, w, this is from the previous one, plus c summation I equal 1 to n, c of I, where c is a user defined positive parameter. So c is defined by the user, and from here we can go to the optimization problem, to the dual, the same way. We follow the same steps as we did, and we found the Lagrange dual of it. So Now the problem will be that dual Q of alpha is equal summation I equal 1 to n alpha I minus half. So we're going to repeat the same thing. However, we have some difference here with the we have a difference in the condition. This is subject to 1. We have I equal 1 to n for alpha I di equals 0, and 2 we have, this is the new condition, alpha I c for I equal 1 to n, where c is user specified. So this is the new problem. As you can see, it's very similar to the normal problem, where however we introduced the c parameter. So c is assigned by the user. So if c has a large value, it has it implicates that the designer of the SVM have high confidence in the quality of the training. So c with big value, we have high confidence. C with a small value, this means small confidence or less emphasis should be placed on the training. So this means high confidence with training sample. So this is the C selection. Now let's try and solve this problem.